Main topic today is on demonstration of energy support from virtual synchronous generator. And the PHIL study will be demonstrated over IIT Roorkee distribution system, that is IIT-RDS. Conventionally, IIT Roorkee distribution system is fed from utility at 33 kV, which is further stepped down to 11 kV. Majorly, there are 8 feeders to which several solar PV panels and different loads are connected. Further, in islanded mode, IIT Roorkee distribution system is energized by diesel generators, and they are close to 6 megavolt ampere capacity. Also, the solar PV panels of 2.8 megawatt capacity and battery energy storage system close to 800 kilowatt capacity expected to be installed, but however, during the simulation we consider that 800 kilowatt capacity of storage system is in place are to be utilized. The considered percentage integration of PV panels and BESS result into 45% integration of non-conventional sources of energy in islanded mode of IIT Roorkee distribution system. Hence, due to such a higher percentage integration, IIT Roorkee distribution system faces low inertia condition. Thus, 2.5 megawatt of virtual synchronous generator is utilized to provide ancillary support, that is inertia and primary frequency response provisions. The efficacy of BSG providing ancillary support can be validated at laboratory level through PHIL testing. In this slide, schematic diagram of PHIL implementation is depicted. Simulated IIT Roorkee distribution system in RTDS is interfaced with power amplifier via DAC. Here, voltage level in RS gate is scaled down to plus or minus 5 volt. Further, VSG is connected to power amplifier. The current output from the VSG is sensed and given as input to RTDS via ADC. In detailed schematic diagram is also illustrated in this slide along with the control strategy of VSG, where its active and reactive power loop are represented by APL and RPL. Grid angular frequency is sensed through PLL and given as input to VSG, which constitutes swing equations as its control strategy. Further, RPL takes grid voltage as input and QV droop acts as its control strategy. Further, power amplifier is energized by an external source via voltage regulator. It consists of one AC to DC converter, which is further connected to 3 DC to AC converters. The sensed current signal from power amplifier is fed back to RTDS. Controlling of VSG and operation of network in RTDS can be monitored at controlling desk. Now, the complete setup which is before you, the PHL setup for this experimentation. As you could see, the simulator RTDS. So, IIT Roorkee distribution network which is burn inside RTDS, and you can see power amplifier, controlling desk, FPGA controller, semicron converters, and IITR network monitoring RTDS routine window, and you can see as MCB. Furthermore, the laboratory test bench in RTDS lab at Electrical Engineering Department of IIT Roorkee can also be visualized in this lecture. It comprises of scaled down hardware prototype of VSG, Here the DC supply is connected to the semicron inverter acting as VSG and is further converted into AC. The VSG is being controlled by FPGA controller, which takes DC and AC quantities, that is currents and voltages, as input with the help of sensors at the back side. The AC output of VSG is connected to L filter, which in turn is connected to power amplifier through MCB. Here MCB is utilized for protection purpose. The power amplifier is acting as node NT11 of the simulated IIT R DSIN RSCAD. This can be depicted in draft file of the RSCAD. This node NT11 is taken out as power amplifier for interfacing scaled down hardware prototype. 4 feeders with their open midpoint connections can be observed. Here the GTAO and GTAI blocks of interfacing hardware prototype can also be observed. Systems SS2 to SS6 can also be depicted, which comprises of different ratings of solar PV panel and load. Subsequently, in order to interface scale down hardware prototype of the VSG, it is firstly synchronized with the grid by enabling PLL. This panel displays 3-phase grid voltage by enabling PLL. It can be observed that VSG voltage is synchronized with grid voltage. Subsequently, current output from VSG can also be observed from this panel. The system is under steady state condition currently. To validate ancillary support by VSG, 2 contingency scenarios are simulated, out of which first correspond to disconnection of solar PV panel N1B of IIT Roorkee distribution system. Here the breaker is utilized to connect and disconnect the solar PV panels. First, it can be observed that system is under stable state as drop in frequency is 0. Also it can be observed from controlling desk that VSG is supplying power. The scaled up power output of VSG in RSCAD can be depicted in runtime. It can be seen that VSG is providing 204 kilowatt of power. Variation in power can be observed since VSG is trying to maintain frequency of the system at its nominal value amidst of intermittent solar PV output. Subsequently, the breaker is turned on, which results into disconnection of solar PV panel. It can be seen from controlling desk of scale down hardware prototype that the VSG has increased its current output. In runtime also it can be observed that the frequency is stabilized to its nominal value, since after undergoing a drop of around 1.1 hertz, as you could see from the diagrams, due to reduction in power availability in system, this is possible since VSG increases its output as shown in runtime to provide inertial and primary frequency response. The second case study corresponds to connection of induction motor. Similar to case study 1, switch SW2 is utilized to connect the induction motor load. Initially the system is stable as it can be observed from frequency drop profile in runtime. Subsequently, the induction loading is increased by turning on switch, hence a dip of 1 hertz in frequency can be observed. Here it can be seen that the VSG has increased its current output in order to provide ancillary support. It can also be observed that frequency returned to its nominal value with the contribution of VSG as it increases its power output from 153 kilowatt to 160 kilowatt in low inertia IIT Roorkee distribution system. The challenges faced while modeling of IIT Roorkee distribution system and PHIL validation are discussed in this slide. Firstly, in order to perform frequency stability study and observe electromagnetic timescale transients, accuracy need to be maintained so that original characteristic of the network can be preserved. The cables are modeled using pi model as only 432 nodes are available, hence the loads which are in vicinity are combined. This also helps in maintaining originality of the system. In order to involve accuracy or in order to involve accurate characteristic of diesel generators, those are modeled using 6th order models. It includes excitation system, power system stabilizer and turbine governor model. While simulating frequency stability study, it is required that voltage remains under limit. It is availed by simulating shunt capacitor been installed in the campus at different nodes. Further, solar photovoltaic converter is modeled in small time step section of RS gate. Precautions need to be taken here to not model PV converters as average models. It is due to the reason that average models do not participate accurately in transient studies as much as small time step section models do. Also, PI controlled twinning of two equal rating converters may not work. This is observed due to interference of RTDS interconnection between rack 1 and 2, that is interconnection between different subsystems through star-star interfacing transformers. In addition, PV module association are also different, which can result into different step responses for each 3-phase converters. With respect to designing of control at FPGA level, it is important to determine appropriate switching frequency for physical DC to DC and DC to AC converter incorporated in VSG converter. Also, interference between inner and outer control loops should be avoided by their appropriate bandwidth determination. It maintains the accuracy of control strategy. Further, proper knowledge of designing counters and desired number of delay blocks are required. VSG is interfaced to power amplifier through filters in order to maintain power quality. TSD need to be maintained below 5% while feeding power into power amplifier. Otherwise, the distorted power can even lead to instability of converter control. Precautions should be taken in deciding LC and LCL filter values in order to avoid resonance conditions. It is important to determine if active or passive damping is required or not. While interfacing the VSG to system in RTDS, it is equally important to decide appropriate value of interconnecting impedance. This is due to the fact that higher value of interconnecting impedance can result into connection to a weak grid. Other probable cause of error during PHIL validation can be enumerated as transformer connection for connecting subsystems, accuracy of measuring sensors and scaling factors relate to it along with scaling factor associated with GTAO and GTAI cards of the RTDS. The described model can also be used for other quite extensive testing scenario such as PHIL testing for increased integration of PV and BSS, co-simulation while involving uncertainties associated with PV by forecasting algorithms and optimization algorithms for volt var control and loss minimization, integrating electric vehicles into the system, incorporating cyber security aspects of the network. The developed controller prototype can also be tested in recreating original operating conditions of the IIT Roorkee distribution system. It can be done by use of the actual component with which controller while cooperate in field scenario. The test setup involves IIT Roorkee DS in RTDS, while a part of it's taken out along with involving real advanced metering infrastructure and GSM communication infrastructure. The concept can be once again described as through the schematic diagram in this slide. Here IIT Roorkee distribution system is modeled in RTDS with 3 nodes taken out with the help of the amplifier. The measured voltage of substation node 7 named transformer is taken out via GTAO card of RTDS. As GTAO output is in the range of plus or minus 5 volts. Hence, amplifier is required so that AMI can measure the AMI1 transfer the data to CLE through communication channel. Further, the scaled down hardware prototype of VSG at node 1 is interfaced to amplifier 2 through GTAO2. AMI2 communicates with LLE, which further provide control signal to VSG. Here LLE also communicates with CLE with GSM. The output current of VSG is fed back to system in RTDS via GTAI cards. Node 6 named as line end is also taken out and its measured data by AMI3 is fed to CLE. Hence, with case studies corresponding to different scenarios, testing of VSG, CLE and LLE can be performed. The PHIL demonstration of ancillary support from VSG can be concluded in this slide with few important lessons learned. Firstly, offline simulation of large power systems can be impractical due to the amount of computational resources needed to solve its network equation. Also, when using RMS test cases, transient present in power system may be neglected or ignored. The modern energy conversion system requires an enhanced level of details for properly representing their behaviors. Moreover, due to the steady increase of non-synchronous generation, new operation and management strategies need to be tested to ensure power system security. These constraints can be overcome by using EMT real-time digital simulations, as it provides high precision results in a time frame suited to a specific study. Clear difference between different simulation tools can be also observed from the below mentioned tables. Next, impedance changes such as cables, transformers and loads behavior cause influence on controller tuning parameters, which could be detected in open loop steps. It was detected at conditions like with and without transformer interconnection between subsystems that shows distinct responses of output voltages and power. Therefore, further studies regarding the controllability of the system should be developed. Converter and DC side electrical elements are modeled with a time step in the range of 1 to 4 microsecond. Rest of the power system is modeled in which a time step of typical time step of 25 to 50 microseconds are considered. It has been observed that lower the simulated impedance and the higher the hardware impedance, the better the stability of the system. Thus, addition of hardware inductance and the introduction of additional interface filters implemented in hardware proved to be helpful. PHIL test gives higher fidelity than simulation only studies and can model real power networks to study a particular phenomena. Further, with the hardware constraints for real time computation, large and complex power system simulation cases requires that electrical model be split across different hardware devices such as split example across CPU cores, and the associated communication implies a time delay between the execution of the network solution at either end of the interface. When splitting electrical system, this delay is often modeled as a Barragon stub line which introduce a section of impedance for which the time for a signal to travel along exceeds one time step to allow time for communication of the signals between devices. Therefore, such time delay should be considered while designing control strategy. These are the following references are being used significantly during the preparation of the presentation, and with this note I thank you all for your kind attention. Thank you. A very good morning, dear student friends, and today we are going to talk about demonstration on peak energy management using storage. Whenever in any power system, as you all are aware that the renewable energy sources are quite intermittent, and with the current scenario they keep on increasing, and the new type of mobile loads presents operational challenges and severe threat to the network voltage regulations. As you all are aware, in India, I mean it has been told that we have more than 4 crores of actually mobile vehicles today, including three-wheelers, and I am very sure in recent past it was very aggressive in the Indian distribution system having more number of two-wheelers and three-wheelers electric vehicles, and in next decade I am very sure the electric mobility or e-vehicle load is going to be significantly high, and that may lead to operational challenges in any distribution system. When the PV output power in active distribution network exceeds the load demand, that the system voltage are expected to rise, and that may lead to reverse power flow in the network, may cause severe challenges in future. Now, if you focus on The standard load curve, as you could see, the blue color load curve, ideally we experience two different peaks in a day, as you could see this point as well as this point. So, one could be your morning peak and the other could be your evening peak. Now, when you have excess PV integration to the network, so then you can see that the mid part, especially during the off peak area, where you have excess renewable PV generation available to you. So, that means your load is significantly less. However, the generation is available to you is much higher than the load, may lead to voltage increase in the system. Now, if you consider this is my main grid and these are the PV connected to the system, and because of the variation in the load generation, I think you may experience a reverse power flow from the load side to the source side. Similarly, when the load demands are high and there is little or no solar power supply, undervoltage might be noticed. These phenomena are quite common on academic campuses of this country, where rooftop solar become a very common installation. For example, overvoltage is often noticed while students in the campus are out for lunch, resulting in low load demand, and at the same time solar power is at its peak. One more interesting scenario academic campuses can experience is especially during summer vacation, where the solar energy available to me is quite high. However, most of the 50 to 60% of the load especially belongs to hostel loads are almost close to zero. Similarly, a significant undervoltage may be observed during the day when the load demand is at its peak due to practical classes and the solar power is rapidly reduced due to cloud transients. As well as at night when there is no solar power available to me and the load demand increase significantly due to different weather conditions, especially in northern India, the night load due to heating is significantly high. Also, it is noteworthy is that a significant portion of the installation takes place in the low voltage residential zones, where the grids are not originally designed to accommodate the interconnection of generating units. Because academic campuses are evolving system, so from the day 0, it has never been planned or expected that the PV installation may be present in any distribution network of an academic campus, but over a period of time storage and significant PV integration taken place in recent period across the country within academic campuses. In case of energy management system present in battery energy storage system, as we discussed, have multiple solutions to repeat voltage control and then handling intermittency in your PV systems, peak load savings and also reduction in losses. Now, this energy management scheme provides an option to maintain the peaks at a specific range and at the same time provides reasonable ancillary support. Now, this increasing prevalence of distribution energy resources, so called DRs installation on the campus network presents system operators with a variety of new opportunities and challenges. It is thus critical that future distribution system operate in a coordinated and integrated manner in order to ensure their efficiency and reliability. And to demonstrate the effectiveness of the peak energy management, utilizing storage in a real distribution system, we have used IIT Roorkee distribution system as a platform to demonstrate our research activity. This is the single line diagram as we have seen at IIT Roorkee, and the distribution network at IIT Roorkee distribution system consists of close to 16 substations with a peak demand is slightly more than 6 megawatt and a minimum of close to actually 2 to 2.5 megawatt. So, that is what reasonably experienced within the network. So, I think theoretically just to highlight, the peak may be between 6 to 7 megawatt and the off peak will be between 2 to 2.5 or 3 megawatt. Numerous load points associated with solar rooftops are depicted in this model. The entire distribution network has different load profile at each time of the day. I think I expect all my dear student friends to go, I mean, slow to understand and repeat those presentations if necessary again and again, because now we are getting into the real implementation of this concept. So, IIT Roorkee distribution system has been modeled in the draft file of the RSCADE for real time analysis. Here we are using the RSCADE version FX 1.1. The 11 kV system is modeled in the first subsystem, whereas the 415 volt network are modeled in the subsequent subsystems. The subsystems are linked via cross rack transformers. The underground cables are designed as a pi section and the loads are modeled as dynamic loads. Solar PV systems are modeled and distributed over the distribution network. To validate the performance of the control strategy of the battery, we will first observe the voltage profile of all the 415 volt nodes in the RSCADE runtime window, and by simulating the entire IIT Roorkee distribution system, the voltage profile at different location for varied solar irradiance, temperature and loads are examined. We have captured screenshots of the maximum and minimum voltages during the 24-hour operation for each session, taking extreme weather and load conditions into account. Some of the load locations shows voltage deviations from the maximum and minimum permitted voltages. Over voltage indicates a high level of PV penetration with a lightly loaded conditions, whereas low voltage indicates a low level of PV penetration with a severely loaded condition at those discovered locations. To limit the influence of voltage variations and therefore the peak energy, it is necessary to incorporate battery energy storage systems into the network. To do so, foremost it is necessary to determine the location and size of the battery energy storage system to be installed within your low voltage distribution network. The optimal size and location of batteries in the IIT Roorkee distribution networks are determined by formulating a mixed integer linear programming MILP problem to minimize the investment and operation cost of the system. As you all aware that installation of battery become an expensive proposition or a solution. So, we need to perhaps very carefully try to optimize those installations so that the overall cost for the network can be minimized. The total problem was solved using Gurobi solver in YLMIP MATLAB interface, and the obtained locations and sizes of the battery energy storage system are shown in the table with the names of the substation at IIT Roorkee. So, I think these are the locations you can see from our network, and these codes are basically the bus numbers, and you could see the energy rating and power rating, and these are the physical locations of the system. So, for some extent you can have priority of 1 to n locations, but depending upon your budget and requirement you can choose best few locations suitable for your installation. The batteries optimized sizes and locations are then used for the active power management of the system by utilizing it for the control strategy. After finding the optimal location and size of the BESS as we have discussed, we have to validate the same using power hardware in loop PHIL experimentations. So, what has happened? You have simulated your network and obtained certain locations for battery installations and also the ratings, and now we need to validate at the laboratory test bed before we physically deploy those uh, solutions or integrating to the distribution network. This is a schematic representation of the PHIL setup that has been implemented at the laboratory level. To perform the PHIL, first of all, we will need a battery emulator. The battery emulator that we are using here is having the rating of 40 ampere hour 200 volts. Battery emulator combined with a regenerative AC to DC converter designed to mimic the behavior of real batteries. The next component is a bidirectional converter with an output rating of 18 kVA. The maximum value for the DC voltage is 600 volts, for the output current is 30 ampere, and for the switching frequency of 20 kilohertz. The following piece of apparatus is an L filter that has a rating of 5 millihenry, followed by a circuit breaker that has a rating of 25 ampere. Here we are utilizing an SPITGen Verger and Spice RL 4000 version power amplifier. This can function in both PHIL and grid simulations. The amplifier has a power rating of 15 kilovolt ampere and its nominal voltage is 230 volt RMS. The RTDS system that is displayed here is made up of 6 different racks, each of which is made up of a number of parallel processing cards. This includes cards for running the simulation as well as inter-rack communication, workstation interface, and input-output cards. The RTDS simulator is a combination of custom hardware and software that is used together to achieve real-time power system simulation for the purpose of performing hardware in loop testing of protection, control, and power equipments. This is accomplished through the use of a hardware in loop testing environment. Here the simulation software package known as RSCATE supports my RTDS is used in the process of configuring the IIT Roorkee distribution system, which is subsequently executed on hardware that is designed for parallel processing. The GTAO and GTAI cards are used to transfer and collect signals between the power amplifier and the RTDS. We are using FPGA powered Xilinx Zinc SoC XC7Z020 controller to perform our control strategy. The controller is equipped with integrated voltage and current sensor that can directly measure up to plus or minus 1000 volts and 25 ampere with internally isolated channels. It is also able to operate the inverters as well as converters directly without the need for any intermediate circuitry by utilizing level shifted PWM channels. It can export or import data signals from external devices using its high speed analog and digital I/O. We will now examine the connection diagram for the battery energy storage system, which will be connected to one of the nodes in the IIT Roorkee network. This will be done with the purpose of enhancing the voltage profile in the network at those periods of the day when the irradiance of the sun is at its peak or highest. Here, the battery emulator has been linked to the input connector of the semicron converter, which converts the DC power into the AC power. A connection has been made between the power amplifier and the output terminal of the BSS converter. The power amplifier is then linked up with the RTDS in order to inject the necessary voltage and currents. This is accomplished by lowering the scale value of the voltage and current signals so that it may be transmitted to the IIT Roorkee network. In addition to this, we have established a link between the BESS converter and the WAVECT controller for PWM connection. Now, we will look at how the WAVECT controller generate pulses with modulation and how the battery energy storage solution contributes to an improved voltage profile. In order to do this, we must first build the fundamental control algorithm in the WAVECT controller. The controller is basically dependent on the previously mentioned FPGA module. In order to put this into action, all that was required of us was to dump the grid feeding converter algorithm into the WAVECT controller using the MATLAB Simulink SDL coder. In the beginning, we will synchronize the BESS converter with one of the nodes of the IIT Roorkee network. After activating the PLL in order to achieve grid synchronization, we are able to observe that the grid has been synchronized with the BESS converter in the right top waveform. After this setup, we will enable the PWM pulses that are sent by the WAVECT controller to the BESS converter. PWM pulses enabling will simply fed the ID reference or IQ reference, that is the real power and reactive power as determined by the peak energy management and voltage profile algorithms that will run on the RTDS platform. Here we can observe that the node voltage of the IIT Roorkee network in left top waveform as 60 volts line to neutral RMS, which has been scaled down by 415 volt line to line RMS for the PHIL experimentation with the help of a power amplifier. Now, we have to observe the charging and discharging profile of the BESS and corresponding power absorbed or injected in the hardware setup at different instants. In the first case, we can see that power is positive in the right bottom waveform, which means it is discharging instant of BSS, and after that we can see that power is negative, which means it is a charging instant of the BSS. This instant has been recorded during the PHIL validation of BSS connected with the IIT Roorkee distribution network. We have physically connected a BSS converter with the IIT Roorkee network, and to implement this we have connected the BSS converter to RTDS with the help of the power amplifier using GTAO and GTAI cards. Now, we can see one of the nodes of IIT Roorkee network in which GTAO and GTAI signals are coming out and coming in from RTDS platform respectively. After carrying out the PHIL experimentation, we observed that the 5 locations that had been identified with the help of optimization tool were able to regulate the voltage and thus manage the peak energy. This is the single line diagram of the IIT Roorkee distribution system, where we can observe that the 5 locations where the 5 battery energy storage systems are placed, one of which is already located in the Department of Electrical Engineering. Now, if you look at the Electrical Engineering Department microgrid architecture, so this is the physical department site, and we have utility grid, and this is the battery which is of lithium ion and close to 200 kilowatt hours, and we do have a rooftop solar installed on the top of the department which is close to 170 kilowatt, and then we have reasonable diesel generator backup from time to time. So, if you see the 3 loading conditions, the rooftop solar which is 170 kilowatt, the electrical engineering department load considered to be 111, close to 111 kilowatt, and then we have a storage of actually 200 kilowatt. So, to us this is one of the wonderful microgrid architecture one can visualize with these ratings and requirements. We will now proceed to the location at the electrical engineering department where the BESS is connected. To optimally utilize the distributed solar rooftop resources, we identified 5 optimal locations for the deployment of battery energy storage devices of capacity close to 800 kilowatt. We have simulated the whole campus and performed PHIL to validate our technology, and further deployed the same at the electrical engineering department, which operates as a microgrid with 111 kilowatt load, 170 kilowatt PV rooftop and 200 kilowatt battery energy storage system. The main functions of the proposed energy storage system will be peak energy management, bidirectional control of real and reactive power, as well as the PV energy smoothing. The upgrade distribution network enables the institution to improve its usage of renewable energy and provide an uninterrupted power supply with enhanced voltage and frequency profiles. Thank you. welcome you all to this NPTEL online course on smart grid. And after a long journey, we are shortly reaching to the last lecture on conclusion. All my viewers, my personal suggestion is to not limit yourself to the course content which has been addressed during last 39 lectures, though they are the basic materials for smart grid, but it's a vast research area where you are expected to also look for different opportunities and scope of learning through other sources of literatures and other web media materials. But as a whole, we tried our level best to cover the syllabus on smart grid. The main emphasis was just to make sure that you understand both fundamentals and the implementation aspect of smart grid. And our experience is limited to the lab scale test bed available in this campus. And I hope for the new learners this is quite enough to understand the basic fundamentals on smart grid and bit of application scope. We started with introducing smart grid in detail, covering all the architectures, the way it has been described in different literatures, the different definitions of smart grid at large. And then we moved to different case studies, the different control schemes, protection schemes, and slowly we entered to different analysis schemes, and we understood what is AC smart grid, what is DC smart grid, what is AC-DC smart grid or hybrid smart grid. So, for all three, AC smart grid, DC smart grid and hybrid smart grid, different simulations, modeling and analysis have been discussed. And at the end, I also wish we have to look for opportunity what currently our country is focusing on smart grid at this stage, and what kind of initiatives government has taken to encourage young researchers to work in this field, and what are the other avenues available for you youngsters to go ahead for research opportunity in this particular field. Now, if you see India's journey in the field of smart grid is quite significant, and if you see today the smart grid objectives of India highlights many goals or desired milestones have been fixed. 35 million smart meters installation by 2019, which is a huge target being fixed. Industry collaboration with ESCO model, which is a very new initiative where energy efficiency schemes are adopted by the distribution utilities. 3 full-scale projects on smart grid executed with by spending 258 crores by now. 40,000 megawatt rooftop PV expected by 2022. Effective use of existing sources. Proliferation of electric vehicles, they are coming in a big way. Smart grid and smart cities are the hot topics. And with this fundamental, certainly I do see that you are learning the course on smart grid under this NPTEL online program, not limit you just as a course, but you can perhaps extend your understanding and be part of this smart grid initiative taken by Indian government. Now, the government of India approved smart grid pilot projects. There are many. The primary goal of the pilot project is to incorporate distribution system with advanced metering infrastructure, AMI schemes, power quality management, PQMs, outage management systems, peak load management, distributed generators. So, you can see there are so many pilot projects are being executed. Most of them have been over and some of them are still in progress. So, we could see that the different pilot projects in the field of smart grid are on way at this stage. Now, the worth is too many, the pilot project cost too much, like 3,816 million rupees have been spent to achieve smart grid outlook through these pilot projects. And there are few pilot projects under NSGM, National Smart Grid Mission, which has also spent 5,773 million rupees at both Chandigarh, Amravati, Congress Nagar, and at Kanpur. The projects are in process. And currently, almost all the leading institutions in the country, all the IITs and most of the central funded institutions today do work rigorously in the field of smart grid. And to mention few, the Indian government has sponsored 5 Indo-UK collaborative projects on smart grid. The first one is Accept HEPAD, Rescue, IMES, and Reconfigurable Distribution Networks led by different IITs. And one of the projects that is HEPAD is being led by Indian Institute of Technology, Roorkee, and all the analysis that I have shared with you is the outcome of the HEPAD project and the support that we have received from the Government of India, Department of Science and Technology. Now, there is one more Puducherry Smart Grid pilot project jointly developed by Power Grid and Puducherry Electricity Department. They had very specific objectives, and the implemented functionalities do have advanced metering infrastructure, demand side management and demand response, outage management system, renewable energy integration through net metering, solar electric vehicle charging stations, and street light automation. And this also quite expansive project at recent time. Now, Chamundeshwari Electric Supply Corporation, Mysore, also achieved a good initiative in the field of smart grid, where the accomplished objectives were 18,076 single phase meters to be installed, installation of 446 DCUs, installation of 3-phase LT-CT GPRS meters, agricultural DSM with community portal, KPI based MIS and data analytics. And this is also a quite successful project at this point of time to highlight the Chamundeshwari project. Then perhaps IIT Kanpur also initiated a smart grid project under smart city. So they have perhaps actually tried to SCADA implementation of substation through RTUs, rooftop solar installations, storage supported grid connected hybrid inverters, and control room development for monitoring. So they have taken a 20 households and tried to execute a kind of what kind of smart grid concept can be extended so that energy efficiency can be achieved. Now, key smart grid facts and figures till 2016, the number of smart meters were 5.2 million and number of electric vehicle registers were close to 6,000. And there are 4 substations which are completely automated, and now many substations are coming up in this direction. Now, I mean, for all the viewers, I wish to also highlight, after learning this fundamental, this is something I shared regarding the kind of opportunities available for you to participate in smart grid activity at different levels from the government side. And also we have identified few research areas that one can choose to continue the smart grid research further. In the line of operation, control and protection, we have different categories which has been highlighted with the support of many experts across the country. Operation and control of large, medium, small scale renewable energy sources, protection technologies for AC and DC smart grids, wide area monitoring, protection and control, energy management techniques, supervisory control of network with multiple micro and nano grids, network analysis and optimal power flow, modeling and simulation of large power grids, seamless grid operation involving TSO and DSO, forecasting of renewable energy and loads, And there is one more important aspect, that is cyber security and ICT, reliable wired and wireless communication technologies, interoperability and ICT architecture, audit and validation tools for cyber security feature, HAN, WAN and Internet of Things, threat models and cyber security, information privacy and handling challenges, cloud computing, data storage and big data analytics. Now, if you move to the device side, what sort of power electronics area one can choose? Fault right through enhancement of converter interface to renewable energy sources, grid interfacing and islanding issues along with seamless transfer technology, ancillary services of converters, optimal design of flexible power converters, coordination and control of multiple converters and modular multi-level converters, converter technology for HVDC and medium voltage DC systems. Multifunctional hardware smart grid enablers, smart and unified control of converters, hot swappable converters for smart grid, standardization of voltage and power levels, network voltage regulation and power quality, wide band gap devices, and finally we come to energy resources storage and deployment issues, policy, regulatory and market design issues, demand side management with optimization and forecasting techniques for storage and renewable energy sources, inertial issues of renewable energy sources with stochastic behavior, optimal mix, siting and sizing of energy storage at various level of the network, electric vehicle interfacing issues for V2G, G2V and V2H, energy storage system for meeting transient and other requirements, and there are so many industries who are currently working on smart grid. So, you can also choose a future with industry, and to name few, ABB, Accenture, Capgemini, Cisco, Kyan, HCL, NDPL, General Electric, E-Meter, Elster, IBM, Infosys, Kema, Siemens, Schneider, Mahindra, Power Grid, Posoko. I mean, there are so many currently focusing on the field of smart grid research. So, I do see a long way for viewers to go ahead if you are taking this course seriously. To conclude the session, I wish to highlight that all the aspects starting from simulation, modeling, theory and understanding and execution of smart grid have been covered in detail. Perhaps we have taken a high level attempt to make you understand the real time simulation of smart grid, and few cases have been discussed in detail. To start with, we have initiated the architecture of smart grid, definition of smart grid, modeling and simulation of smart grid, analysis of smart grid at all three levels of AC smart grid, DC smart grid and hybrid smart grid, and to end up with their applications, we have considered different case studies like demand management, demand side management, demand response, load flow analysis, coordinated voltage control schemes through both hardware and RTDS simulation platform. We have analyzed all the case studies for your benefit, and to make a better understanding of your theory, we tried our level best to cover the syllabi as maximum as possible. Hope this course will certainly help you to make you understand the background, concept and application on smart grid at large. Thank you very much.
Well, so now with this we end with Day-20 of our FDP, and I discussed with sir Today we will be sending you the quiz tonight, right? We will post on WhatsApp also, and it will be available on Canvas for next 2 days.